So hello everybody, my name is Roger, I work for PSI Audio and we make speakers, loudspeakers, but we've also developed a low frequency active sound absorber that works extremely well on typically on room mode. So what I'm going to explain to you today, or try to explain, is that a little bit about room modes, how much they are an issue and a pain, and that there are solutions and that active solutions are much more effective than passive solutions. So just a little bit about the company. It was founded 40-something years ago by Alain Roux, who's now retired, and his aim was always to reproduce sound as accurately as possible and do it in a scientific way and not in a subjective way, and he's always been developing speakers like that. He's now retired, but we continue with the same DNA in the company. So he started with passive speakers that were used quite a bit in that are used quite a bit in hi-fi and also pro audio. Then PA speakers, we also develop and manufacture a brand called Rowan, and then we developed the first active speakers we did here for Studer. So we sold those, well, we manufactured them as an OEM until 2003. And then since 2003 we relaunched our old brand, and we've been selling that, and in 2015 we, thank you, 2015 we started selling this sound absorber. So I always like starting this presentation, you all know it, but I always like starting with a few figures about sound. So you know that sound is basically pressure going up and down, pressure waves going up and down, but you also have an associated movement, velocity of molecules going back and forth. It travels at 340 meters per second. That means that sound will go back and forth in a room like this 8 to 10 times per second, so it travels a great distance. Frequencies we hear 20 to 20,000 hertz. That means you go from wavelength from 1.7 centimeters to 17 meters. That is almost the length of this room. So the difference in size, in physical size, is quite enormous. Then the pressure levels that we have, we can hear between about between 0 and 120 dB. 0 dB corresponds to 0.0002 Pascal, which corresponds to 0.0002 millimeters water column, so it's absolutely minute. And normal listening pressure would be 80 dB, that's 0.2 Pascal, and that corresponds to 0.02 millimeters water column. That corresponds to 20 millimeters air column. So if you move your head up and down 50 times per second, you will hear a sign or something at about 80 dB frequency. And all of this, we hear it, so they all mixed up, so all these different pressure waves coming from all over the place, they all come to your ear at the same time, and you can hear minute variations over the atmospheric pressure that is 100,000 pascals. So it's absolutely minute, and the sensitivity of our ear is fantastic. And we decompose all of this in frequency, phase and amplitude to be able to determine the source of the sound, what it is, the environment we're in, and where it's coming from. So we've got quite a complex instrument that we use here. Now, what we know about good listening rooms, that include mastering rooms, of course. So we've seen this a few minutes ago already. But of course, what we hear, we have the direct sound that's going to come directly from the source to your ear, and this has all the information on the origin of the sound, what it is, if it's a twig cracking or if it's somebody tapping on a snare drum. But then you have all these, the room influence, so you have all these early reflections and the reverb that come into consideration. So when we make speakers, we will calibrate them in an anechoic environment. That means we don't have all of these, and we can make sure it's absolutely correct. Your direct sound is absolutely correct. So that's the most important thing, is to have a very accurate direct sound. And then all of these early reflections and reverb, they give you a sense of environment in which you're in, and they're very interesting and important to identify where you are and where the sound is coming from. But of course you can see that the amplitude and how well they're distributed is very important. Also important to understand here is if you're doing like a measurement somewhere with a sweep, that's basically a continuous sound going up more or less fast, all of these sounds will be mixed up together, and that's not at all how you hear most of the impact sounds and transients, where you will hear the direct sound and a bit later you'll have all of this. Okay? Now, this is what happens when you measure it, and then the way you perceive it is again completely different. Okay, so first of all, the first reflections, if they're very short, you'll identify it as one single source. And this Here you can see all of this going up to about 10 milliseconds, but a good sound engineer can differentiate down to 1 millisecond. So I'd say underneath 1 millisecond, so that's a few tens of centimeters away from a wall, the first reflection, yeah? And then you have the Haas effect, where basically you will hear the first reflection, but you'll be able to concentrate on the first sound and and analyze this first sound without making abstraction of the rest. Then you have the first reflections that come a bit later, and they are very interesting to understand the sense of environment you're in here, okay, for example. And if it's too loud, it gives you an echo that's annoying. And then, of course, then there's a reverberation. So just to understand what happens here is you don't have one microphone when you hear. You have, for start, you have two ears that are separated by about 20 centimeters that get different information that you can analyze. They don't work like a microphone, and you don't listen to sweeps most of the time. We often want to measure a sweep and think that's also the frequency is important, but you cannot forget about the time domain. That is extremely important. Now, as I said, again, direct sound gives you an indication of the source of sound qualitatively and where it is, and it must be as accurate as possible, extremely important. The indirect sound enables you to understand what environment you're in. It's the sum of all the reflections that are there, and the best way of measuring easily these secondary or these reflections is the RT60, and that's the time it takes for the reverb to go down by 60 dB. I think you're all familiar with this. And it depends on the size of the room, what you're listening to. But you can have, for example, in a church where they were built without amplification, you have a reverb time that is very long, 5 to 10 seconds sometimes, which is fine. It's not a problem as long as the acoustic message is quite slow and short, and the reverb has time to go down before the next message comes up. In a studio, you have to listen to much faster music, and the reverb time has to be much shorter, typically 0.2, 0.5, up to probably 1 second. But it must be similar or balanced over all the frequencies. You don't want to sound like a studio or sound as if you're in the mountains in snow, totally anechoic in the high frequencies, and then feel as if you're in church with the low frequencies, which is unfortunately what happens in many rooms. Okay, so what is a good listening room? Well, first of all, you need a room, because you need to have a sense of environment. Otherwise, you'd be listening in an anechoic environment in the mountains, in the snow, or in an anechoic chamber, which you feel a bit lost because you don't get the sense of environment. It's a lot more comfortable having a bit of echo from the room. And the room has to sound natural, so that it's like this one reverberates quite a bit, but it's the same in all the frequencies. Now, frequency response. Most importantly, you need a good distribution of these first reflections, not that they all come in at the same time and at the same frequency, but it has to be a flat frequency response at the listening position with a sweep is not the goal to have. It's a consequence of a good room, yes, but that's not what you should be seeking to. You have to incorporate the time domain. Listening position within the critical distance, that means that the direct sound is louder than the reverb. That's also important. Time response, so this is what you have to measure, is the RT60 in a mastering studio, 0.3 to 0.8 seconds, I guess, everywhere. It can go a bit higher in the low frequencies, but it should stay quite low. You can go a bit dead, even a bit deader in a studio. And this is, of course, easy to obtain in mid-frequencies, high frequencies, but very difficult in low frequencies, which I will explain also. Now, room modes, diffuse modal behavior of sound. I guess you all know about room modes, but room modes is basically if you're pushing a kid on a swing, if you push the kid at the right time, you're in phase, and he keeps on going. If you keep on pushing him at different times, he won't get a good movement. So room mode is when the frequency or the wavelength of the frequency corresponds to the dimension of a room, and it'll ring for a lot longer, a very long time, and lose energy much slower. Okay, this is all understood. Now, of course, you have first modes in different dimensions, so you have width, length, height, and you have here, you can see typically the pressure distribution, where you have a high pressure at the end. So if you have 20 hertz, for example, you've had very high pressure over there, and you'll have low pressure over here. Or the second mode, you'll have high pressure, low pressure in the middle, and high pressure over here again, yeah? So these are the kind of room modes you're talking about on the sides. And then you have combinations and second modes. So instead of pushing the kid on the swing every time. You'll push him every second time. So you let him go once, and then you'll push him every second time. That's the second mode. If you push him every 3 times, he comes back. That's the third mode. It's a good image to understand how it works. So this is a perfect shoebox. This is a room that's 7 by 5 by 25, so quite a big room already. And you can see that the modes go from 25 to 100, 150. You can go quite a bit higher. But what you do notice is that there's zones where the pressure is high and zones where the pressure is low. In general, there's between 30, 50 or even more room modes in any room that you have to treat that are below the Schroeder frequency. Schroeder frequency is the limit between where room modes are disturbing and when there's so many of them and so close that they are not disturbing anymore. Okay, so room modes are a real pain. They're so difficult to treat, a lot of you just work with it and live with it, but there are solutions. But first of all, as we see, the pressure distribution is uneven in the room, so it creates peaks and nulls at different frequencies. They resonate for a lot longer, so when your kick has stopped, it continues resonating for half a second, so it's sound that's not there. And while it's doing so, as it's low frequency, there's a lot of masking effect of the higher frequencies. So the fact of having a room mode, a low room mode, it'll mask and create a muddy masking effect on the higher frequencies, and that shouldn't be neglected at all. The other thing is that they're very difficult to control because they're generally between 20 and 150 hertz, and they cause errors for sound engineers who are hearing their room more than what's coming out of their loudspeakers and their mix. Okay, so here we have the kind of typical pressure distribution over different frequencies in a single place, and this is a waterfall. So you see here on the top line, this is the frequency response, and then the frequency response over time. And you can see that these room modes, they resonate for a lot longer than, for example, the rest of the time. And this is all this time where it's resonating, it shouldn't be there. You're hearing something that's not there. You're hearing the room, and it's masking a lot of the higher frequencies. So they are a real pain. Now, just the difference between diffused sound is what's above this Schroeder frequency, and modal behavior that's underneath this Schroeder frequency. So diffused sound, typically the wavelengths are small and they act a bit like ripples in the room. So you can see these little ripples, they go in all directions, they get diffused very, very quickly. And the result of that is you have a pressure distribution in these frequencies that is very, very even over the whole room. Result of which you can put a square meter of absorber anywhere in the room. It'll have approximately the same effect on an RT60. So it's quite easy to treat things that are higher up, yeah? And then the modal behavior is when the wavelengths are big compared to the room, and here you should imagine a tsunami in a bath or something like this, where it just goes woof, woof, woof. And there you can imagine that it'll get into all these artificial waves in swimming pools. You can see that there's places where it's very high or not. And here, well, there's the distribution of pressure is very uneven in the room, but the good thing about this is you can treat it where the pressure is highest. And you can have a leverage effect on the treatment of this. And this is very typical to room modes. Okay, here you see the room mode distribution here for a typical room, well, the same room. And you can see all of these room modes. The Schroeder frequency here is around 135 for this room. Above this, they're so close together, they don't really bother you. But how well they're distributed here is very important. Unfortunately, that's to do with the size and geometry of your room, and it's not very easy to change. But it's very important to have them well distributed. If you have a cubic room, you'll have one that will be 3 times the size somewhere in the middle here, which is to be avoided. Okay, now, how do you treat reflections? You've understood that the room and the indirect sound is all to do with reflections, and we want to treat them. So how do we treat them? So first of all, we want to understand, well, just a little bit about acoustic pressure. That's the pressure going up and down. But like when you're swimming in water, you have the waves going up and down, but you also move back and forth. And this is the associated velocity that goes from high pressure to low pressure. Like when you have high pressure and low pressure, you have wind in between, and this is the same in acoustics in the alternative back and forth world. Acoustics is, I studied mechanical engineering and thermodynamics and a lot of fluid mechanics, and acoustics is fluid mechanics in alternative world, going back and forth, nothing else. Anyway, so you have this velocity. So, of course, energy conservation dictates that when the pressure's high, the velocity is low, and this is also quite understandable. When the pressure goes high, the differential is not very big, so there's not much movement. But the result of all this is that the velocity is out of phase from the pressure. And when you're against a wall, the conditions at the limit dictate, if the wall is rigid, that there's no more velocity, and all the energy is pressure. Okay. The speed is never very high because it changes direction, but the acceleration can be quite high, and there can be quite a lot of energy in there. Now, against the rigid wall, as I said, the pressure is zero, and whatever velocity there is there has to change into pressure. Okay, so there's no more velocity, and everything is pressure. So against the wall, if the wall is rigid, everything is transformed into pressure, and this creates a peak in pressure, and that creates an echo. That's exactly the mechanism of a reflection. And I think this illustrates it quite well, where you see these people. You can imagine these guys, I don't know what they're doing, but anyway, but you can imagine them going up and down with the waves, but also going back and forth with the swell. And the movement of water, when it reaches the wall, what happens with it? Well, it goes up. It has nowhere else to go up and create pressure, which will create a backwards movement. And this is the mechanism of the reflection. So how do you do to avoid this? Well, the first thing you can do is move the wall, change the geometry of the wall so that the echo goes in another direction. But you're not really reducing the amount of energy, you're just sending it somewhere else. But that's one thing you could do, or you could have disperse it a bit more, that's one thing. The other thing is you should imagine here the water going quite fast. What you could do is slow down this speed. So you could imagine you planted lots of trees here. You could slow down this velocity so that when it reaches the wall, it's almost stopped and it doesn't transform into pressure. This is typical to porous absorbers where the speed is slowed down in the material itself. Okay, and you can imagine that when the waves are very long, you need to have quite a few trees. So you need a lot of trees if the waves are long. And the other thing you could do is leave the geometry as it is, or this wall, but move the wall back and forth in frequency with this velocity. So there you could avoid any of these waves crashing. This is quite easy to understand, difficult to materialize, but it's quite easy to understand. So you could do this with a kind of flexible wall that goes back and forth, or you could actively move the wall back and forth. So this is active absorption, when you actively pull the wall back and forth. Okay, so that gives you a good image. 3 ways of controlling reflection, just to summarize: modify wall geometry, but this doesn't remove any energy, it's just changed the angle. You can slow down the acoustic velocity with porous material, or you can make the wall move passively with the resonators, or actively with active absorbers. Okay? So the geometry that we use, diffusion is quite used very often, but you should also think that a diffuser that has a size like a few tens of centimeters is not going to diffuse wavelengths of 10 meters. So they have to be very big if you want to affect room modes or other things. Now, porous absorbers work very well, but you have to slow it down where this, as you could imagine before, slow it down where the speed is highest. So typically, you want to put the porous absorber a quarter of the wavelength away from the wall for it to be effective. Okay? So typical alpha factors of a porous material will depend on the thickness, and then it'll be very effective just underneath 1, and then suddenly it'll go down. Okay? So porous materials, they work very well for higher frequencies where the wavelength is short. So here, just an example, when you have 100 hertz, the wave is 3.4 meters, so you need a thickness of 85 centimeters so anybody who sells you a bass trap that goes down to 58 hertz that's this size, it's not a bass trap. It doesn't work at those frequencies. So as I said, it works where the velocity is high. I think this you understand. Yeah, one thing to understand also is that the sound will go many times through this material, so it'll have a multiplying effect on it. Now, absorption, so you imagine these waves coming against the wall, and the wall can move. So this, of course, something passively, like any window is an absorber, or a door, anything a bit flexible, and it'll absorb very well on its resonance frequency, because that's the frequency, it's going to move naturally very easily. So that's very easy, but that means you have to tune it for a single frequency. Yeah, so there's different Am I going too fast? Do you understand this? But there's different ways of tuning Helmholtz resonators, membrane resonators, but they'll typically work on their natural resonance frequency only and need to be tuned to do so. And you can make them more or less effective or more or less broadband, but basically that's all you have to play with. Now, active absorption is when you have an engine and you move this back and forth. Of course, in acoustics, it's very difficult to move a complete wall back and forth very quickly and very accurately. So what you can do is displace the same amount of air or same amount of water, but over a smaller area. So you should imagine displacing the same amount of water or air on a small area, which means you're going to be pulling water or air from a wider distance. So here you can start imagining how a small device can be more effective than its own dimensions. What you need here is you're increasing the velocity, the speed is higher, and you're creating an acoustic impedance, which is a ratio between the pressure and the velocity that's a lot lower than it is in its natural environment. So this is how we can do it. So basically you can measure the height of the wave and say, for this height of wave, I have to move so much volume of water or air to avoid the reflection. And this is exactly how our AVAA works, is you have a microphone, that's a very good device to measure pressure, and this is of course a membrane, because we know how to make those move very accurately in frequency and phase. And we only have a few centimeters to be in phase between what's measured here and what comes here. So here we've always achieved better results with analog technology, and the latency we have here is between 0.2 and 0.3 milliseconds. So you have to be extremely accurate and quick if you want it to be in phase. So this is basically how it works: a microphone, a membrane behind it, then we have pressure to velocity conversion that moves this, and then we also have a resistance, an acoustic resistance with very small holes, that first of all it dampens a bit of the feedback you can get between the membrane and the microphone, but it also acts as a bit of a conversion between pressure and velocity. If you have pressure in front of a wall with holes, what comes out the other side has higher velocity but less pressure. So we're converting part of the pressure into velocity and absorbing it here. But the aim of this is to keep zero pressure or very low pressure in this chamber inside of it. That's basically how it works. So I'd like you to remember that it's not noise cancelling, that it's absorption, it's active absorption by imposing a low impedance that has an effect bigger than its own dimensions. So this is how it works. We impose 100 pascals per meter, so the impedance goes up to about 400 over about 1.5 meters, and this means that this is the free field impedance. So what you see a window about this size, the portion of the surface of this sphere, or this portion of sphere, of 400. That means the effect is like opening a window of this size. It works between 15 and 150 hertz, because that's where we have the most room modes, and we can have an equivalent absorption up to 25 times the surface of the object. This is just some simulations we did to find the best impedance, the perfect impedance. You can see that we're not extremely sensitive to impedance, somewhere between, I would say, 50 to 150 something. So it's extremely difficult to measure all this. Now, those who've tried to measure movement of air in those frequencies, you'll understand. So we had to develop the sensors that go with it, plus the way of calibrating the sensors. You can't just invent a technology and then let it go. Anyway, then this is also the simulations on how effective it can be. I'll just go quite quickly. This is also the range. And of course, if you put it in one corner where the pressure's high, it's going to be extremely effective. If you put it in a place where the pressure's low, it won't be that effective. Anyway, so you tend to put them here, 2 of them to keep them symmetrical. Behind the monitor, you're going to be absorbing the reflections earlier than if they go to the back wall, so they tend to be more efficient behind. This is quite obvious. And now I'll just show you a few examples of rooms. This is one where we could manage to compare some big bass traps like this with the AVAA. This is without anything, so it's already quite a good room with 0.2, 0.3 RT60 down to the bottom, but a lot of energy here and quite a bit here, and these big dips also. So this is what happened with this device in all corners. It was quite effective here because that's what it's tuned to absorb, but no impact lower on. And with the AVAA, basically you can see we removed a lot of this energy. This has come up, this dip also, and there's a lot of energy has come up over here. So broadband really. Here we go up to 100 hertz, 120 hertz. This is Bob Katz that tried them, of course, and he bought some. So you can see this is his the frequency response, and you can see that he has a good room. Everybody would said it's a good room, but still, it's not flat. Don't try and have a flat room response. Try and have a natural one with the RT60s that are quite good. So he tried them, and he bought 3 sonically, blah 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 blah. What he says, I never thought it could be attained without some serious compromise, usually an overdamped room in the mid and high frequencies. That's also a great advantage, as you can treat the low frequencies without overdamping the high frequencies. You can treat the room modes without messing up your mids and highs. Okay, he bought 3 of them that he put in the corners at the back, plus 1 in the middle that treated one of the lengthwise ones. This is a student, Michael Feller, that did a diploma in Switzerland, and he put them basically in a type of garage where he measured different types of bass trap that are here, basically with nothing, with one type of bass trap, with the other, and with the AVAA. And this is the RT60. So he was about 2.5 seconds, and by turning one of them on, he got to 0.6 seconds, and by putting it in the optimal position. And this is the same exercise without putting it in the optimal position, so just putting it anywhere, where it brings it down from 2.6 down 0.1, 0.4. So what we can see is even if they're not optimally placed, they have quite a good effect. And you can see that they're much more efficient than any of the other bass traps he tried and measured. This is Andy Hong. Lots of people will have heard of him also in his room. So you can see the brown is without the AVAA and the blue is with it. So basically it does smoothen out a bit of the frequency response, but it also shortens a lot of these reverb times. And I think he summarized it very well. In short, there was not enough boo in the bass, but way too much oom, clouding the overall image. Once we turned on the AVAAs, we could all hear the boom clearly, and everything else in the mix too. So I think that's what you should remember from this. This is Barry Rudolph, lots of people know. So here, he just sent us his frequency response, and he had a big dip that was obviously due to room modes and that it managed to treat perfectly. Also, the shape of this frequency response shows that it's something that's going to resonate for a long time, okay, and that's been reduced a lot. I arrive at mixes faster with much less of a struggle, blah, blah, blah. Mixes translate even better now. This is another example we got from somebody, Steve Greenberg. Dramatic improvement in hearing separation in the bass instruments and greater mid-range clarity as well through masking effects. Don't neglect this masking effect. This is our room at home where it's extremely obvious when you hear it. It doesn't translate as well here. You don't see it that much, but it's extremely obvious when you hear it, and you can see it a bit better here. There's these frequencies that resonate for a long time. They get a lot shorter, and here you can see the shape of the wave recorded, where here you need a lot longer to get down. So our experience, well, for a start, it's extremely difficult to calculate a room and modelize it and to be absolutely accurate with any type of system. You have a lot of trial and error is necessary to improve your room. Most rooms are well treated in the mid-range, but lack any type of real treatment in the low end. They all have issues. All rooms can benefit from more low-end treatment. There's lots of paper on this, and basically everybody agrees that it's impossible to over-dampen the low end. You've always got too much of it. Resonators are complex, treat single frequency and fixed. Active treatment always improves the low end and perception of the mid and high frequencies. How much is it valued for you in your work every day? That's you to see, but there are solutions if you are bothered by these room modes. We think it's one of the best investments you can do to improve listening quality. Conclusions, people say, well, it reduces, treating the room modes reduces the timing, so they resonate for not quite as long. The pressure distribution and frequency response is much more even in the room, and also the location of the source of the sound, as you have less indirect sound compared to direct sound, your stereo image, and you'll be able to place the kick properly in the right position and things like this. Okay, I think I've said everything I wanted to, and I would only be repeating myself if I read all of this. Yes, another advantage is it looks like this. Right at the end you have a picture of it. That's approximately the real dimension, so it's something about this size, and it'll absorb low frequencies up to something the size of this window. And you can take it with you. We have lots of customers that use them in their live room, take them into their mastering room. When they do off-site recordings, they take them with them. So I hope I've managed to explain a little bit about the problems with room modes, and that there are 1 or 2 active solutions that exist, and it's all patented, by the way, so we like keeping that way. Thank you.